Now let us come to the other parameters of the antenna. One parameter is radiation efficiency. How efficiently the antenna is radiating, based on that this is defined. The used power value is the only difference between gain and directivity. What does this mean? This means that in the gain and the directivity, the power that we are using is the difference. We use different power for gain, for defining gain, and a different power for defining directivity. So for gain, it is a comparison with isotropic antenna. For directivity, it is the antenna in a particular direction, radiation in a particular direction. For example, for directivity, the directivity is the gain of an antenna would have if all input power appeared as radiated power. That is P in is equal to P. This is what is gain. So this is what is directivity. The gain an antenna, the gain of an antenna, if whatever power we are giving as input to the antenna is radiated, completely radiated by the antenna. There is no loss. Antenna does not consume any power. Everything, the power that is given to the antenna is completely radiated by the antenna. Then the gain is same as the directivity. The gain, so this is what is directivity. Whereas gain shows us real antennas and nearby structures, they consume some of the input power, and that comes from the gain. All real antennas are made up of mostly metallic objects or dielectric objects which has a loss. Dielectric object which has a complex part. There is no perfect dielectric, so dielectric has a complex relative permittivity. Therefore, actual gain, it shows that real antennas and the structures which are nearby to the real antenna, the antenna that is radiating or receiving around that, there will be other structures, so they will consume some amount of input power. Accordingly, the radiated power is determined from the radiation efficiency. That is why radiation efficiency comes into play, because some of the power is consumed by the antenna itself, since it is a ohmic element. Then the other structures which are near the antenna, they consume some amount of the input power. So complete input power is not radiated. So if I give some input power and it is not radiated, if it is completely radiated, it is 100% efficient antenna. But if it is not completely radiated, then the antenna is not 100% efficient. So how much it is radiating, that will determine how efficient the antenna is. So our radiation efficiency determines how efficiently an antenna radiates. That is what is radiation efficiency. We define it as, sometimes some books you will see it is as eta R or eta, or some books you will see it as E. E stands for efficiency, ER is radiation efficiency, or eta also is a common symbol for efficiency in physics. So either eta or ER. Here we are using ER. ER is equal to P by P in. P and by P in, that is equal to P by P plus P0, where P0 is the ohmic losses, P is the radiated power or power. Then since PER is equal to P by P in is the input power, Input power is the radiated power plus the loss. So ER is equal to P by P plus P0. Now in the denominator you have P plus an additional term P0. In the numerator you have only P. Therefore ER should be less than 1 or less than equal to 1. When it will be equal to 1? When if P0 is equal to 0, it will be equal to 1 P by P. If P is equal to 0, then ER is equal to 0. So the limit of ER is equal to 0 to 1. So 0 less than ER less than 1. So 0 less than equal to ER less than equal to 1. This is the limit of radiation efficiency ER. Now we know what is directivity. Directivity D is equal to UM by U average. So a maximum intensity by average intensity is directivity. That we also defined as UM maximum intensity by U average is P by 4 pi. So UM by P by 4 pi. That we define as UM by P in. P. Now for P we can write ER is equal to P by P in. So P is equal to P in into ER. Let us write that. So UM by P in into ER divided by 4 pi. Now UM by ER into, in the denominator we write P in by 4 pi. P in by 4 pi is UM by P in by 4 pi is G. G is the gain. So that is D is equal to G by ER. Since UM by P in by 4 pi is the gain, by definition of gain, this is what is gain. UM by power input by 4 pi, or 4 pi UM by P in is the gain. If you remember that, 4 pi times U maximum by P of power is the gain. So UM into 4 pi by P in is gain. So that is why we have written G divided by ER. So D directivity is equal to G by ER, or G gain is equal to D into ER. So once you know the efficiency, if directivity is given to us, we can find out what is gain. If gain is given to us, we can find out what is directivity. And now let us dissect the intensity. We define the intensity. Now let us dissect the intensity. So here you can see we have an antenna, which is the yellow portion. Here if you look at the yellow portion, that is one antenna that is connected to a transmission line. So on the transmission line or waveguide, whatever it is, so a guiding structure. Antenna is connected to a guiding structure. What does that mean? It means that we have a source of power. That power is going to give, from that power, that source generates the power. That power is given as input to the antenna. So the source is connected to the antenna through a guiding structure. So there is a guiding structure which guides the power from the source to the antenna. Now at the input point where the guiding structure is connected to the antenna, that is the input point to the antenna. So at the input point, power will come from the source to the input point and it will go to the antenna. Now if the guiding structure, the characteristics impedance of the guiding structure and the input impedance of the antenna are complex conjugate of each other, then the power will completely go to the antenna. Otherwise there will be some reflection, some amount of power will go back towards the source. If there is some reflection of the antenna, then this is due to the mismatch of the impedance. So at the first point, once you generate some power, some amount of power is reflected back towards the source because of the impedance mismatch. So that part you can see in the green, we have written reflection loss due to impedance mismatch. So reflection loss means loss in the power. So due to and loss in the power, why the loss occurs? Because of reflection. And why reflection occurs? Because of the impedance mismatch. So we write this as reflection loss due to impedance mismatch. Then once it comes to the antenna is an ohmic structure. Since it is an ohmic structure, there will be ohmic losses or loss due to heat. So loss as heat I square R. So loss due to heat will be there. So that is written in the red. So ohmic loss due to the conductor or due to the conductivity of the antenna, there will be some amount of loss. So the power, some amount of power is lost because of reflection mismatch, because of the impedance mismatch, because of reflection. So suppose power is 10 watt. So out of 10 watt, suppose 1 watt is lost because of the reflection. So 9 watt has come to the antenna. Out of those 9 watt, let us say 2 watts are lost in heat. So ohmic loss and due to the conductor is 2 watt. So what is left is 8 watt. So 8 watt power is going to be radiated in the antenna now, and there will be ohmic loss in the dielectrics of the antenna. The antenna will be containing a dielectric unless it is free space. It may contain a dielectric, it may have a dielectric coating, etc. So there will be a loss in the dielectric. So ohmic loss in the dielectric, let us say, that is again about 1 ohm. So 1 watt. So from 10 watt, 1 watt for reflection, 2 watts for conductor loss, then 1 watt for dielectric loss. So 4 watts, total 4 watts. So now you have 6 watts. So there will be 6 watts power which will be radiated. So although we generated 10 watt of power, the antenna is radiating actually 6 watt of power unless there are other losses associated with it. So E0 or the total radiation efficiency E0, that we can say E0 is equal to E gamma. E gamma is the radiation efficiency E gamma is the reflection efficiency. So it is reflected, some amount of power is reflected. How efficiently power is reflected is given by E gamma. So reflection efficiency. Then E sigma is the conduction efficiency, how efficiently it is lost in the power is lost in the conduction. Then E epsilon is the dielectric efficiency, how effectively or efficiently power is lost in the dielectric. So E sigma, E gamma into E epsilon, that is E0. Now we write usually radiation efficiency ER as E sigma into E epsilon, and reflection efficiency ER E gamma as E gamma is equal to 1 minus gamma square. Why it is 1 minus gamma square? The reason is simple. 1 is the unit of power. So 1 unit of power, out of that gamma unit of power is reflected back. So what is left is 1 minus gamma square. So therefore it is E gamma is equal to 1 minus gamma square. So this is about radiation efficiency. Then we will come to something called beam efficiency. The beam efficiency is defined as the total power in the main beam to the total radiated power. Why it is called undefined in this manner? Because we said that the antenna is radiating electromagnetic wave as a beam. As a main lobe, it is radiating through the main lobe. So in the main lobe or in the main beam, most of the power is concentrated. But there are power in the other lobes, side lobes, back lobe, and there are also power. So total power, total radiated power is concentrated in the main beam, then in the side beams also. Therefore, on the efficiency, how efficiently it is radiated in the beam, that is the total power in the main beam by total radiated power. So beam efficiency is total power in the main beam by total radiated power. That we can, in mathematically, we can write it as integration over theta from 0 to theta, integration over phi from 0 to 2 pi of the radiation intensity u theta phi, integration over this beam area, which is sin theta d phi, and that is the total power in the main beam. Then total radiated power is 0 to 2 pi, integration 0 to 2 pi, integration over pi over phi, 0 to pi, integration over theta. Now look at the difference between the numerator and denominator. Over theta, in the numerator it is from 0 to theta. Why it is from 0 to theta? Because the beam spreads from theta 0 to theta. Therefore, it is from 0 to theta. Whereas in the denominator, it is from 0 to pi, because we are not considering the limited zone of the beam. We are considering the total radiated power. Therefore, total range of theta, which is from 0 to pi. Otherwise, the integrands are same: u theta phi, sin theta d phi. Integrands are same in the numerator and denominator. Only there is a change in the integration limit. In the numerator, integration limit is from 0 to theta. Theta gives us the beam width. So this is how we define beam efficiency. Be is equal to total power in the main beam by total radiated power. Then we have discussed about polarization of electromagnetic waves. Since we have discussed about polarization of electromagnetic wave, the same concept holds here, so I am not going to discuss it anymore here. What is linear polarization, what is circular polarization, or what is elliptical polarization, what is right-handed circular polarization, what is left-handed circular polarization, what is right-handed elliptical polarization, what is left-handed elliptical polarization. This figure shows you an animation of these types of polarizations, and what is meant here in the antenna by polarization. What we mean is the field radiated by the antenna or field received by the antenna is polarized in which manner, whether it is polarized in linearly, circularly, or elliptically. So accordingly, based on that, we can define the antenna to be a linearly polarized antenna, to be a circularly polarized antenna, or to be an elliptically polarized antenna. Now you can see here, this is an example of a microstrip antenna. A microstrip antenna radiates a linearly polarized wave. You can see on the in the figure, you have a microstrip antenna, and there is a wave which is propagating, which is linearly polarized. Electric field is in the z direction, magnetic field is in the y direction. So electric field is in the y direction, magnetic field is in the x direction. Propagation is away from the microstrip antenna in the z direction. Then you can see another figure, practical antenna, polarized antenna, which is a circular microstrip antenna. You can see there are 2 points where we are feeding this antenna, and because of the 2 points, one is the electric field, the other is also the electric field. One is the feed of current, other is also the current, what we say, with the same amplitude but 90-degree phase difference. So if they are of same amplitude, 90-degree phase difference, then that will give rise to a circular polarization. So you can see that the wave that is polarized by this antenna is a circularly polarized wave. And then comes what is called the polarization losses. So suppose we are considering an antenna, and incident angle is or incident polarization is like this. So we have a vertical polarization in air is incidented. Then we are receiving the antenna. We have an receiving antenna. So we have a plane wave. Initially, we have a plane wave which is vertically polarized. It is coming towards the antenna. Polarization of the antenna is P antenna, which is slant. It is not exactly vertically polarized. It is slant to the vertical polarization with an angle theta. So it has a P Rx with the slant polarized vector can be decomposed into two components, Prx and P loss. Why it is Prx and P loss, that I will tell you later. But as I told you, Tx stands for transmission, Rx stands for reception. So P antenna is receiving this plane wave. P incident is being received by P antenna. So P polarization of the antenna, which is receiving the P incident, should be oriented along P incident. Otherwise, there will be P incident dot P antenna will not be equal to 1. So so P incident dot P antenna should be equal to P incident into P antenna. It should not be equal to 0. So since it should not be equal to 0, so you will take the component which is along the P incident. So along the P incident is Prx, receiving antenna. So that much will be received by the antenna. What will be lost, which is P loss, which is orthogonal to P incident. That part antenna will not receive because the electric field is not oriented properly along the antenna. The electric field should match. If the electric field does not match, then it will not be received. So if it is orthogonal, then it will not be received. So P loss, so the part which is not received is lost. Therefore, it is P loss. So Prx, P antenna is divided into two categories. So one is Prx, one is P loss. Angle between Prx and P antenna is theta. Now, how we can define polarization loss factor? PLF is called the polarization loss factor. PLF is equal to P incident dot P antenna square. PLF is equal to P incident dot P antenna square. So that will be equal to P incident into P antenna into cos theta square. So P incident square into P antenna square into cos square theta. Now cos square theta can be maximum value of cos square theta is 1, minimum value of cos square theta is 0. Accordingly, PLF will be between 0 and 1. So limit on polarization loss factor is between 0 less than equal to polarization loss factor less than equal to 1. In terms of dB, if we express polarization loss factor in dB, this will give us polarization loss factor in dB is equal to 20 log 10 into P incident dot P antenna square. So this is what is PLF in dB. Now its range will be from minus infinity will be less than equal to PLF in dB less than equal to 0. So on this, from this what we understand is that if there is a polarization mismatch between two antennas, the antenna is the polarization of the antenna and the polarization of the electromagnetic field received by the antenna, if they are not matched, if there is a mismatch between the polarization of the antenna and the polarization of the electric field being received or being transmitted by the antenna, then there will be a loss because of the mismatch of the polarization. And that we have seen why there will be loss or how there will be loss, that we have just seen using analysis or analytically we have seen this. So this is called the polarization loss. This loss is to be taken into account when we do a budget or when we do an analysis of the antenna system or a transmitting and receiving system. Now we'll come to something called phase transmission formula. So to understand phase transmission formula, let us consider two antennas. One is a transmitting antenna on the left hand side. Let us say the antenna is transmitting antenna. On the right hand side, let us say there is a receiving antenna. The transmitting antenna and the receiving antenna are separated by a distance r. If they are separated by a distance r, then the transmission formula, phase transmission formula is PR by PT. PR is the power of the received antenna. So the power received power is PR. PT is the transmitted power. So from the transmission, if PT is the transmitted power, and the receiver, if PR is the received power, then the ratio of these two is PR by PT, that is equal to 1 minus gamma r square, which means 1 minus gamma r square is because of the impedance mismatch loss. So 1 minus gamma r is the reflection coefficient at the receiving antenna. Similarly, gamma t is the reflection coefficient at the transmitting antenna. So when the antenna is connected to the transmission line, so there the mismatch occurs, impedance mismatch occurs. Because of that, the efficiency goes down. So that efficiency is 1 minus gamma square that we have already seen. So here it will be 1 minus gamma r square for the receiving antenna. So you start, 1 minus gamma t square, we start with the transmitting antenna. So for the transmitting antenna, its efficiency will be 1 minus gamma r square. So 1 minus gamma t square. So 1 minus gamma t whole square. Then into gain of the antenna is Gt. Then into 1 minus gamma r square is for the receiving antenna. Then gain of the receiving antenna is Gr. So this will be there. Then in the path from the antenna, transmitting antenna to the receiving antenna, in the path there will be a propagation loss. Since it is propagating, so there will be a propagation loss. That propagation loss is lambda by 4 pi r whole square. That is the propagation loss factor. So lambda by 4 pi r square, that into polarization mismatch factor. So PLF. Now, and this is the complete phase transmission formula. Now, if we consider the complete phase transmission formula, in this formula we can simplify this a little bit. We'll assume that gamma r is equal to 0. There is no mismatch, impedance mismatch, either at the receiving antenna or the transmitting antenna. So therefore, those two factors will become 1. 1 minus gamma r square will become 1. 1 minus gamma t square will become 1. So those two factors becomes 1. So what is left is lambda by 4 pi r whole square into PLF into Gt into Gr. So that also we can simplify. We will assume that there is no polarization mismatch. So if there is no polarization mismatch, then PLF is again 1. So if PLF is 1, then PR by PT is equal to Gr into Gt into lambda by 4 pi r square. That is the simplest formula for phase transmission formula. So PR by PT is equal to Gr into Gt into lambda by 4 pi r square is the simple simplified phase transmission formula. But general formula is this. You can either use this formula or the simplified formula. So with this, we come to the end of the antenna parameters. So we'll take a break here for 5 minutes, and when we come back, there is no time for the other part to be studied. So, if you have any doubts, we will discuss that. Otherwise, any problem है कौन सी? Problem करें. Yeah, problem. So, if you have doubts, any doubts on what we have studied up to this point, or what we discussed up to this point, that we will discuss today. Otherwise, in the next class, I will revise what we have already studied, the